Next, let us go with the ideal filter characteristics. Ideal means perfect. But practically it is not possible to get this kind of ideal filter characteristics. Okay, then what is a filter? As you already know that a filter is a frequency selective network. It allows some frequency components. This is a filter. It is allowing some frequency components and rejecting some frequency components. Some frequencies are allowed, some frequencies are rejected. That means a filter is called as a frequency selective network. Okay, allows some frequencies, rejects some frequencies. Okay, then what is an ideal filter? Ideal filter is something which is having a sharp cutoff. Let me draw the low pass filter. Ideal filter, ideal low pass filter will be having a frequency response like this. See, if you carefully observe, this is 1 and this is modulus of h of omega. This is omega. So this is omega c, this is minus omega c, this is 0. And remember that for all the filters, the phase should be linear phase. Okay, theta of omega should be linear. Okay, for distortionless transmission, the phase should be always linear. Remember that during these points, the phase should be linear. And if you carefully observe, all the frequency components ranging from 0 to omega c will undergo they are multiplied. All the frequency components are multiplied with the 1 up to omega c. Okay, and all the frequency components, that means the input x of omega, I am saying x of omega, the frequency components beyond the omega c, they are multiplied with the 0. Here this is a 0. Okay, so the spectral density function of x of omega, that means the frequency domain representation of x of omega, would be affected by this h of omega. All the frequency components up to omega c are multiplied with 1. All the frequency components in the x of omega beyond omega c are multiplied with the 0. So that means it's a low pass filter. It is allowing the low frequency components up to this cutoff frequency, and it is all rejecting all the frequencies beyond the omega c. Okay, so this is having a sharp cutoff. That means it is not allowing all the frequency components beyond omega c. But practically this will not happen. Practically, a low pass filter will be like this. Okay, so practically, see, if you carefully observe this, there is no sharp cutoff for the low pass filter. Okay, it is coming down like in an exponentially manner. Okay, you are not going to get practically this kind of characteristics. Okay, so that's why they are called as ideal low pass filters. This is all about a low pass filter, that too ideal low pass filter. And the mathematical representation of the transfer function is modulus of h of omega is equals to 1 for all the values, that means omega is less than omega c. So we can represent that his modulus of omega is less than omega c is equals to 0 modulus of omega greater than omega c. Okay, that is this modulus of omega means that is for minus omega and plus omega. Minus omega c2 plus omega c, it is equals to 1, and beyond that omega c, that means less than omega c, greater than omega c, it is equals to 0. I can write commonly like this. This is for a low pass filter, but practically remember that this kind of sharp cutoff will never happen for any practical filter. Practical filters, low pass filter characteristics will be like this. And coming to the high pass filter, this would be the high pass filter characteristics. Okay, the high pass filter will be like this, and anyhow remember that for all the filters the phase should be linear. Okay, if you carefully observe, the high pass filter is allowing all the frequencies beyond omega c, and it is rejecting all the frequencies less than omega c. It's a high pass filter, and the practical high pass filter would be like this. This is a simple RC network, simple RC network which acts like a high pass filter. This is simple network, so you will be having some complex high pass filters as well. Okay, so this is having a characteristics like this. Practical, these are the practical characteristics. Okay, and this omega c would come around here. This is a 3 dB point, 3 dB frequency point, and this is omega c. Okay, all the frequencies beyond omega c are freely allowed through the system. That means this is h of omega, no, this is h of omega. The x of omega spectral density function would be affected by this h of omega. Okay, if the x of omega contains any frequencies less than omega c, they are multiplied with this, and any frequency components x of if any frequency components beyond omega c, they are multiplied with this. So that means in some way the output is affecting by the h of omega. Remember that always h of omega affects the frequencies of x of omega. Okay, that means all the frequencies here, see, all the frequencies beyond omega c, they are freely allowed. All the frequencies less than omega c, they are getting attenuated. Attenuation means they are rejecting, or we can say that reducing the energy. Okay, this is all about the ideal low pass filter, and this is a practical low pass filter characteristics. Okay, when coming to the h of omega, modulus of h of omega, mathematically you can represent as modulus of omega is equals to 1 for modulus of omega greater than omega c, is equals to 0 for modulus of omega less than omega c. But anyhow, for all the filters, the theta of omega, that means the phase function should be linear, that is minus omega t times Td. Next, ideal band pass filter. Next one is ideal band pass filter. Ideal band pass filter will be having a frequency representation like this. Band pass filter, see here, this is a band pass filter, a band of frequencies will be like this: omega 1, this is omega 2, minus omega 1, minus omega 2, this is 1 modulus of h of omega. Okay, all the frequencies between omega 1 and omega 2 in x of omega will be multiplied with this 1, and all the frequencies in x of omega greater than omega 2 and less than omega 1 are multiplied with 0. Okay, remember This is all about the ideal band pass filter. You will be having, when we connect the low pass filter and the high pass filter, you might be getting a band pass filter. Okay. So the mathematical representation of a band pass filter is modulus of h of omega is equals to 1 for modulus of omega less than modulus of omega 2 is equals to 0 for omega less than modulus of omega 1 and omega greater than modulus of omega 2. So that is the ideal band pass filter. Next we shall move on to the ideal band reject filter. Ideal band reject filter, you will be having the frequency response h of omega is like this. Okay, this is omega 1, this is omega 2, this is minus omega 1, this is minus omega 2. All the frequencies in x of omega between omega 1 and omega 2 are multiplied with a 0. Okay, all the frequencies in x of omega less than omega 1 and greater than omega 2 are multiplied with 1. So that means it is allowing all the frequency components less than omega 1 and greater than omega 2, and it is rejecting all the frequencies between omega 1 and omega 2. And remember that these all the filters that we discussed now are the ideal filters. Ideal filters means which is having sharp cutoff like this, sharp cutoff. Beyond omega 1 it will not allow, less than omega 1 it will allow. But practically this will not happen if you design using any practical component. If you will not get this kind of a sharp cutoff filter. Okay, so coming to the mathematical representation of a band reject filter, modulus of h of omega is equals to 0 for modulus of omega 1 less than omega 2 is equals to 1 for omega less than modulus of omega 1 and omega greater than modulus of omega 2. Okay. Next one is all pass filter. All pass filter is having modulus of h of omega is equals to 1. That means the filter characteristics will be like this. Then why do we use all pass filter? All pass filters will nowhere use it for the attenuation or amplification, but they are used for introducing some delay. All the frequency components should undergo with the same delay, and remember that all these are having a linear phase. Okay, for a distortionless transmission, the phase should be linear. That means all the frequencies should undergo with the same delay. Okay, that should undergo same delay. Okay, so the all pass filter you use it for introducing some delay, but not for the amplification or attenuation. So that's all about all the ideal filters. Next we shall move on to the causality and Pauli-Wiener criterion for physical realization.